Okay, welcome everyone back. I see that the numbers are still pretty large. So, okay, so what we did last time, so the ending was a little slightly improvised, so today it will be more prepared. So, recall. So we did some symplectic geometry. So recall some notions that we defined. We said that this is symplectic, symplectic manifolds, where this is manifold. This is a smooth two form on M, satisfying the closure condition, and omega non-degenerate. And if you remember what this meant that if I sit at a point, the manifold M, and I take any element in there, and I plug it in the first slot of omega, so this is the same as I use the contraction, and this is now expecting to eat another vector, so in other words it produces a covector, and in this way we get a map from T to T star, and we want that this is an isomorphism, so that's what non-degeneracy meant. Maybe strategically, let me say that last time it was a bit fast because it was a recollection. This is also sort of like a half recollection because maybe not everyone is super familiar with this, so I will be like slower. But then once we start the main part, then we will really proceed like at a reasonable pace. But today already I will try to make it kind of less fast. Okay.
Your aim is finite dimensional all the time, right?
Yes, finite dimensional. So far, at least like the first half of the lectures.
Yeah, because you need a dual, right?
Sorry?
You need a dual.
Yes.
But you can do it like also,
And the field that we will be using throughout most of the stuff, actually maybe apart from today, it's real numbers. But today we will be using also a little bit complex later on. Can I store this here? There I have some colored plots. So, this was one notion. The other notion that we had was a notion of a Hamiltonian vector field. So if you take a function f, and we can take the differential to the minus, and then we, using this isomorphism, we know that there exists a vector field which reproduces this. So this is the Hamiltonian vector field. And what else did we know? We know that we can define Poisson brackets. So here there will be a small overlap with what Thomas was telling us before. So this is defined in that way. And we know that we also showed that, we didn't really show, but we said that smooth functions on a symplectic manifold with Poisson bracket formally algebra. So from Thomas's course, we also know that this thing has an algebra structure by point-wise multiplication, and we know that they are compatible. So this is actually more than a Lie algebra. But for now, we will need the Lie algebra bit. And we also showed that, as Branyo recommended, to say that this is a derivation. So it satisfies this property. Okay, and that's roughly where we ended. So this was part 1.3. Symplectic geometry, so we are still going to develop that a little bit because I find it generally useful. Is there any course running at the same time about symplectic geometry? I hope not.
I don't.
Okay, great. That's perfect. Then let me cover some stuff here because I think it's generally interesting, and also we will kind of need this sort of thinking later on. So the plan for today, I can say that's the plan is to finish the symplectic geometry bit and then say a little bit about Poisson geometry and complex manifolds. That's the bits which we will need, and then at the end, if there is time, then we will start with Courant algebraics. Okay, so let's prove a couple of small cute propositions. So one which we started yesterday, but we didn't prove it. So proposition: if you take two Hamiltonian vector fields for some two functions and you commute them, then this is this is a new vector field, which the claim, the proposition says that this is again a Hamiltonian vector field, and the function that you get here is precisely the commutator. So, a small proposition, and the proof of that is kind of cute. Right here. So we start by how do we want to start? So recall the definition of this object using this property. So this object is such that if I insert it in omega, then I should recover d of this guy. So let's start by calculating the right hand side. So let's calculate what this is. Okay, so what is this? So first of all, the bracket is defined as the Hamiltonian vector field of f acting on g. But that's the same thing as, I mean, because this is Hamiltonian, this is a vector field acting on a function, so I can just as well say that this is the Lie derivative with respect to xf acting on g. Okay, yeah. So now the Lie derivative commutes with pullback, sorry, with the differential. So this is minus dg, and now I use this thing for g. So I use the fact that dg I can rewrite in terms of its Hamiltonian vector field, and this thing is isg omega. And here I use the fact now that that recall that symplectic form is preserved by all Hamiltonian vector fields. So if this thing would be acting not here but directly on omega, then it would be 0. So hence I can just for free put a commutator in here. Okay, because the other order is 0, because Lie derivative xf equals omega. And now we use one of our propositions from before. We know that this is nothing else but the Lie derivative of, or the commutator of this object and this object. And looking at the beginning and at the end, we see that this vector field that's here is precisely by this definition is the Hamiltonian vector field for the brackets, commutator, the Poisson bracket of fm. This concludes the proof. With this little playing with these Cartan formulas. And we saw before that as a corollary of this we have that there is a map. That the natural map from here, which you take a function and produce spits out the Hamiltonian vector field, and we now know that this is in fact a morphism of Lie algebras. So this is a Lie algebra morphism. Okay, so that concludes this chain of propositions that we had the other time. And since there is no symplectic geometry coordinate, I think this is a nice place to mention this other cute thing, which is valuable to know in by itself. So this is the so-called Liouville theorem, which says that let's say let m omega be symplectic. Let's say 2m. We know that it's even symplectic. And then the claim is that then the flow of any Hamiltonian vector field, so that the flow of xf preserves the natural volume form that we have present here. Which is simply 1 over normalization, and then I wedge omega with itself n times. Okay, so the proof of this is, well, nothing else, and that's just, let me just call it omega n. With this, it's the end of the proof. So you get a bunch of omegas, you act on them in the Lie derivative, which is the thing that generates the flow. And using the Leibniz property, we can just move this to act on individual omegas, which is 0. Now, the proof is easy, but the statement itself is kind of deep. What it says is that, this comes from Hamiltonian mechanics, that if you have like your phase space and you have some sort of area, some volume in there, and you let these things evolve along the Hamiltonian equations, which precisely correspond to the flow of such a field, and this thing will flow somewhere, And the shape of the shape can change, but you know that the volume stays the same. So it's cool fact. And of course we won't need it, but it was kept. Why not mention it?
Is it in Arnold? This picture with the cat?
Yeah.
Sorry?
There is a picture of that with the cat in Arnold's book.
Ah, okay. Okay, I have to look this up.
And then we make a soup of that.
But there is also the cat map, right? That's also,
Yes.
but that's different. Is it?
It's different.
It's different. Okay.
But you like the cat.
Right. Okay, so I realized I didn't give a simple example of a symplectic manifold. So let's take R to n, and let's pick some coordinates, which I will strategically call xi and pi, where I goes from 1 to n. And then I will take omega to be dpi dxi. And remember that we are summing over repeat indices. So this is really the sum of things. So in a sense, this is really just a like a direct product of many R2s, each of them carrying the simple symplectic form, and then I just put them together. And it's easy to see that this satisfies the properties that it's closed, because it's exact actually, and it's non-degenerate because essentially all the coordinates are entering here. So this is symplectic. I will call this example somehow because we will need it. So let's call it, I don't know, star. Maybe that. Okay. Any questions about the example? Okay, good. Okay, now let's make a small definition. Because so far we talked about symplectic manifolds, but as is proper these days, one has to say what the morphisms are, not just the objects of some interest. So in here it seems that the most natural notion that you can have is the so-called diffeomorphism. So we said that diffeomorphism phi between two symplectic manifolds. I don't like subscript, so I will just call it omega on both sides. Is called symplectomorphism. If, well, the symplectic form is pretty good. So if you put it back, you get the symplectic form on the left. And you see that this is kind of like a, okay, this is a sort of, okay, well, so if you have symplectic manifolds of different dimensions, okay, so this is a sort of map of symplectic manifolds, but unfortunately it's already an isomorphism. So if you have two such things, then it's a diffeomorphism. So kind of there is a long-standing subject of like trying to define morphisms of general symplectic manifolds in some reasonable way, and there are interesting ways that one can go, but I will not talk about it probably. Not today at least. So let's just stick to this one, and now let's prove the main theorem here. Again, so theorem. Which says that every symplectic manifold locally looks like this. Every symplectic manifold is locally symplectomorphic. To the example star. So this is kind of a big theorem with large and far-reaching consequences. So locally just means that I have my symplectic manifold, and that around every point I can choose a small enough neighborhood, which is symplectomorphic to a small enough neighborhood of this model example. The whole body, of course, it's not the case because the subject will be pretty boring. So, okay, this is an important theorem, and its proof is also very useful to know. It employs what is called a Moser trick. Moser's trick. By the way, it might not be immediately obvious, but these statements will be useful for us for courant algebra, so I'm not just proving it out of
So there are many things you can prove using that kind of thing, right?
Yes, that's right. Yeah, so this is a general useful thing. Although I'm specializing in this case, but hopefully it will be clear how to generalize. So let's say that we take our symplectic manifold and we pick a point there. Now, okay, note one thing that I think we discussed. I know we haven't, but we will. Okay. So if we are okay at this point, we have our omega at that point m, and this thing is a two-form. It's a closed two-form at that point, and we know that it's antisymmetric, and we know that it's non-degenerate, and because we know that such things they have a normal form, so we saw that you can always choose coordinates such that it looks like this kind of block diagonal matrix with this kind of 2 by 2 bits. So all such things are equivalent. I mean, you can choose a chord. You can choose frame where you make it look like this, for instance. So okay, so what I want to use is the fact that we can now pick coordinates around, local coordinates around this point. I will call them x and p. Picture here, some point m. So we are picking some small chart. And my first claim is that we can pick coordinates x and p such that then we can define a new symplectic form, which will be dpi dxi. So this has a priori nothing to do with our previous omega. But I'm just saying that pick some coordinates, and once you have the coordinates, then just construct these two forms. The claim is that I can pick this such that this thing will coincide with omega at the single point m. Okay, so this is a much simpler statement. I'm just saying that I can take this small local thing, and I can I have some two form defined there, and I'm just claiming that I can construct coordinates such that this new thing, which will be tied up to the coordinates, will coincide with this at the point. And the reason I can do that is just we can do it, I guess, constructively. You just take this thing at the point m, which is some two form, find a frame in which this two form looks like this. So you have a local frame. Sorry, just a basis. So just find a basis in this vector space, which gives you this matrix for this guy, this component. And once you have a basis, once you have a basis at the point, you can extend that to a coordinate neighborhood. So that's what I'm doing. Okay, so this is just sort of there's nothing deep in this. So the punchline is that now we have two symplectic forms. They are both living in some neighborhood of the point, and they coincide at the point. Okay, and so now what I want to do, I want to show is that there exists a diffeomorphism, local diffeomorphism. Everything is now in that neighborhood, so local. Diffeo of that local. I'm a bit sloppy with the notation, but I'm now focusing only on this local neighborhood U. Okay. So there is a diffeo such diffeo phi such that pulling back omega, we get omega tilde. Okay, and once we show this, then we are done. Because then we just show that our on our patch, the original symplectic form, if I pull it back, it becomes this thing. So it's precisely this local model in this chart. Okay, is that clear? interrupt me. Okay. I will assume it's clear. Let's prove this. This is now a relatively general looking statement, but it is a cool proof. So now, what will we do? So how do we do this? So define. So let's do this. So we define a family of symplectic forms, a family of forms, omega depending on time, on some t, some parameter. And I will define this simply as this kind of linear combination of 1 minus t times omega tilde plus t times omega. Right. Okay, so this is a family of two forms. Now, are they antisymmetric? Yes, because there are two forms. Are they non-degenerate? Because in principle, things could go wrong. But it's precisely at this point where I'm using this fact that note that this family, at whichever time, if I look at point M, then because this thing and this thing are the same at point M, then these terms cancel and I just get this is omega at M. So I know that whatever this thing was, that point M is always non-degenerate. And hence, okay, then I can potentially, if I restrict it to a smaller neighborhood, I should be able to I can assure that this thing will be non-degenerate throughout the whole interval 0 to 1. D was it 0 to 1. Okay. Maybe after shrinking U, the interval, I can always make sure that omega t non-degenerate for all t. Okay, so now we have a family of symplectic forms. So now what do we do with the family of symplectic forms? Well, we will use it to continue the proof. So, okay, now we have a family, and now let us look at the time derivative of that family. So what is it? So t here is just, it's an external parameter, just 0, 1. So what does it give? It's not a tricky question. This is the definition. Sir?
Just the difference.
Yes. Does everyone see that? If I take, this is just like basic calculus. There is t here, there is t here. I take the derivative, the t goes away. I get 1 times omega minus 1 times omega tilde. I see you are too shy, so maybe I need to ask more. Okay, so this is constant. I mean, independent of t, fortunately, but it doesn't actually matter. But now I use the fact that we are doing stuff locally, and so because we are doing stuff locally, we know that this is closed, and this thing is exact. So there exists one form in that neighborhood which will satisfy this. Again, potentially if the neighborhood was small but not contractible, again, there is shrink it further to make it contractible or something. Anyway, locally this is true. Okay. So now I will use the last thing. So now we will define a family of vector fields. Y of t. Using the fact that at each time t, okay, I define a family by requiring that if I stick them into omega at that time, I will recover the sigma, maybe the minus. Okay, so remember, we have a family of symplectic forms, They are non-degenerate, so I can use them to relate tangent and cotangent bundles, spaces, and hence I just have a bunch of one forms, so I can transform them to vectors at every time. Okay, now I have a family of vector fields, and now I can flow along them. So let phi t be a flow along this family. So now note that I mean this is slightly different than what we saw the other day. Like this is the we now have a we are flowing along a family of vector fields which depend on time, but that's I mean that's fine. It just means that you know like you're sitting at a point at time 0, you move along the vector that the corresponding vector at that point at time 0, you move a little bit, and then you look at what vector sits there, but also you move in time. So you look at you know it's an equation where you have like dx over dt is equal to y t minus x, except that there is an extra time here now. So it's not a what is the thing called interbernal time, autonomous or something. Okay, so now it's not, but it's fine. So let this thing with the flow along that, and now the final step, we calculate the following thing. Now finish. Let me swap it again. Complicated logistics. Okay, so now let us calculate the last bit. Let's check what is the time derivative of this thing. So at every point we have our family of forms, we have our flow, let's pull it back. This gives some other form, and let's calculate the time derivative of that. Okay, so just using the chain rule or Leibniz or whatever. So this is the same, but there will be a term where I take this guy, so this is phi t star of the time derivative of omega t. And there is a bit when this thing hits the flow. And maybe without going into more detail, what happens here is that you will get the flow, and then you will get a Lie derivative along the vector field, which I call y of omega t. Okay, so if I hit the flow, it should be some infinitesimal change of the flow, which normally corresponds to Lie derivative, but now because I'm not differentiating it at time 0, but in more general time, I also get this thing. Let's ignore that for a moment. It's you can figure out details if you want, but okay. So now we are almost done. So now let's write what this is. So using the Cartan magic formula, what will I get?
It's the d of d integral.
Yeah, d of I of t, because and the other term I don't get because omega is closed. That's how we constructed them. They were all closed. Okay, but then let's look at back. So what is this thing? By the formula that's directly above it. This thing is just minus d of sigma. And what is this thing? Looking there, it's d of sigma, right? What a coincidence. So this is 0. Okay, so you see that this quantity, this symplectic, this form that we have here, which depended on time, actually does not depend on time. So we can compare it at various points, and the most certain point that we can do is our point 0 and 1. So this implies that phi 0 pullback of omega 0 is the same as phi pullback at time 1 of omega 1. Okay, this just follows from the time independence. Now let's substitute things. So what is omega 0? Okay, now I will wait for until anyone says so. What is omega 0? And this is the definition of omega.
Omega tilde.
Thank you. Omega tilde. What is phi 0 star? What is phi 0? So specifies a family of flows starting from 0 to 0 and
It's identity.
its identity. So I can just note everything here. But what is omega 1? Thank you. And whatever, this is something. And now we got the thing that we wanted to prove. That there exists, that we can build up a diffeomorphism which pulls one form and the other. Okay, that's the end. It's called Mozart's trick. Start now. Any questions? I raise one of the boards. Maybe I think I should say is that for those that are enrolled and are planning to take an exam, is that since we are going to cover quite a lot of ground, I won't be requiring everything on the exam. I will pick up some like bits that I will emphasize that they are important, and by no means everything, because as you see, it's already. If you haven't seen these things before, then it might be quite a lot of things. I will be mostly focusing on this Courant algebra business that comes afterwards. So do not despair. But if you like this, then any other questions? Okay. Really, no questions? Everything's clear and exciting.
So maybe.
Yeah, please, very good.
I kind of thought we are looking for the symplectic between the U, with the form locally, and the actual R2M with the and so what we really found the vector field, which kind of seems to be still on the same.
Yes, very good, very good. But good question. But here I'm using the fact that the other form was constructed in terms of these coordinates, which means that when I say that I have coordinates, it means that I have a coordinate chart, so it means that I have a map from this one to R to N. So there's a psi. So technically speaking, I should precompose it with psi or postcompose it. So that's how I get to R to N.
Okay.
Thank you. That's a very good point. Very good. So more symplectic geometry. So further example. So now we know that, okay, yes, by the way, from the fact that we know that the Arrow theorem is kind of a strong statement. It says that locally symplectic forms, they all look the same, maybe up to dimension. I mean, because they can live in R to N, so N can be an integer. But up to, they only depend locally on dimension. Otherwise, their form is locally unique. Which means that there is, like, in particular, the subject is usually called symplectic topology. So, in a sense, emphasizing that there's like not really kind of topology is the thing that's interesting in juicing. Like, what kind of topology can the manifolds have that have these kind of structures? It's also kind of rare for objects to have this kind of local property. So we will see Poisson geometry in a moment, and that one certainly doesn't have the local form of such strength, at least. Okay, so now let's take any manifold. Let's build some more topologically interesting examples. That's what I'm going to do. So now that we can take its cotangent bundle picture, M, and we have cotangent bundle. It's a vector bundle. At any point here, so we take a point M, and the point is a fiber above. This can be described by specifying where I am on the base, and then where I am in the fiber, but the fiber is simply the cotangent direction here. So here, the point in here is described by a pair of M and P, where here P is a cotangent vector. It's a covector at that point. Okay. So now what I want to do, I want to construct. I'm finding that this is always symplectic. Again, most of you have probably seen this. But how does this work? So first of all, we will define one form on the total space. So up here. And so how do you define define it like the following? So how do you specify a one form? You specify specify how it pairs with stuff. So suppose that our form theta is sitting at the point M and P. Okay? So here I have a tangent space here and corresponding cotangent space. That's what I'm looking at. Okay, and now I need to plug in a vector. I need to plug in a vector that's sticking somewhere here. Vector, V. I need to tell you what this thing is. So this should be a number, right? And the only way to get a number out of this data that I have, namely no data essentially, is that I use this projection to project this vector down. It's called pi. So I project it down. What do I get when I project? Sorry, push forward. Push it forward down, so I get something that in the picture it will just simply be the same vector but projected down. This one. And then well, this is a vector, so how do I get a number out of the vector? What is the thing that I need to write here such that the result is a number out of these ingredients and nothing else? P. Thank you. So this is a vector. I created it with a covector, which I have, just this P, and the result is a number. And this defines one form here, and then I just claim that, okay, let's see, proposition is that cotangent bundle with the symplectic form that's defined as d of this theta is symplectic. So there's a canonical symplectic form of the cotangent bundle. Now, what is the non-trivial claim so far? Well, we already know that this is closed because it's d of something, and d of something is always closed. What one needs to check is that this is actually non-degenerate. But that's also not terribly difficult. And in particular, one way to see that immediately kind of is if you do this everything in coordinates. So let me call it, okay, let's say it's an exercise, which means that I won't do it, and if you're interested in it, you can try to do it yourself. Exercise. So once we pick coordinates, local coordinates on the base, on M, let's say xi. So this thing in particular will induce a frame of the cotangent bundle. So this thing will give us coordinates on T star M, which people typically call x and p. And then you can show from the definition above that this theta is nothing else than pi d theta I. And hence omega in that coordinate neighborhood is just dpi vxi. So in that coordinate neighborhood is precisely of that form, which I erased, but R2n. And hence you can see that it's not degenerate.
Theta should be
omega, sorry, x. Good. Yeah, here I obviously copied it correctly. Thank you. Okay, so this is kind of the most, well, unfortunately this is not compact. Why is it not compact?
Vector space.
Yeah, because fibers are vector spaces which are not compact. But apart from it, it can be kind of topologically non-trivial, so it's not just R2n normally, but it can be something more fancy. Okay, so before finishing, we need to mention something about Lagrangians. So let's talk about, let's make a small subsection which I will call subspaces. Submanifolds. The this is the last kind of interesting bit of symplectic geometry we will need. Maybe apart from reduction, which maybe we will cover later on, but not here. Okay, so let's make a definition, and let's start by doing things linearly in a vector space. So let's define an analog of symplectic manifold. Let's say that a symplectic vector space is a vector space V equipped with a further bottom, equipped with an element in the second power with dual. So we call it V, so it will be here. Which is non-degenerate. Full stop. So I won't require any closure or anything because here we are doing this vector space linear analysis. So this is kind of before going into manifolds when you can require things to be closed or whatever. Involve derivatives. Here this is just linear analysis. So this is just a very silly notion where I'm just it's an element like this. In particular, I know because non-degenerate locally it always looks the same because we have a normal form. Okay, but it's a good toy model. So for instance, example, M omega is symplectic, then and all tangent spaces with the corresponding omegas are symplectic vector spaces. They are a bit more because you can, if you put them all together, then they assemble into an omega which lives everywhere and which is satisfying some non-trivial differential constraints. But in particular, every point we get a vector space. Okay, and now definition. We say that a linear subspace, a vector subspace, how is it called? Vector subspace U inside V is, and now I will define four notions at once. So we call it isotropic if V, sorry, U, U is the big small space. U lies in its orthogonal complement. Okay. I realize that. Okay, so let me define what I mean by this. So here, using color chalk, U perp is simply defined as all the vectors in vector space which are orthogonal, symplectic orthogonal to everything, meaning that so they are. If I pair them, so if I see this omega as some sort of pairing, then I want that they're orthogonal to whatever I put in U. Okay, you're familiar with this notation where I use the whole set here to just denote that I mean that this is true for all elements of that set. So great cheating notation. So in other words, this is what you expect it to be. It's the orthogonal complement, but here instead of metric we use this omega, which is still non-degenerate, just as a metric would be. So okay, so what does this mean? So if I break it down, what does it mean that it lies in orthogonal complement? This means this is the same thing as to say that this means that any element in U is orthogonal to everything that's in U. In other words, the whole of U is orthogonal to the whole of U. Which is the same, again, as saying that if I take omega, no, the thing I wanted to write is not true. Okay. Yeah. Okay, that's it. And in particular, we see that having an isotropic subspace means that this isotropic subspace has to have dimension which is at most half of the dimension of the whole space. V. And that's the reason for that is that irrespective of what I use in the calculating the orthogonal complement, if I use metric or symplectic form, if you just look at the system of linear equations that you are getting for calculating this, it always follows that the dimension of a subspace plus the dimension of its orthogonal complement, it's always the dimension of the total space. This is true. Even though this subspace might be sitting inside this, or this subspace might potentially be sitting here, or even though they might have a non-trivial intersection, from the linear algebra it always follows that as far as the dimensions are concerned, they always sum up to the full one. And hence, if you look at here, knowing that U sits inside U perp means that the dimension of U is smaller equal to the dimension of U perp. And plugging that in here, is it obvious? Yeah, probably. Good. So that's isotropy. Now there is a corresponding notion of coisotropy. We say that a subspace, but again, we mean the subspace of this. We don't go to duals. We just, for this notion, we really just talk about subspaces of a given symplectic vector space. So we say this is coisotropic if this inclusion holds the other way. And this in particular implies that the dimension has to be larger than half of the dimension of V. So things to remember that coisotropy is big and isotropy is small. That's kind of remember it. It's a useful mnemonic. Now what happens is you see that these things there is precisely one possible intersection of these two conditions, and that's what's called Lagrangian. So if you say that the subspace is Lagrangian, that's kind of the most important notion. If U equals U perp, and this in particular means that the dimension of U has to be precisely one half of the dimension of V. And okay, I wanted to fit a fourth one, but okay. Kind of a fourth one which goes kind of orthogonal to this is called symplectic. So you call a subspace symplectic if, when you restrict omega on to that subspace, this is still non-degenerate. So it's kind of, you want that the restricting, you also get a symplectic subspace. That's why it's called a symplectic subspace. What is the condition of the dimension in this case?
It has to be here.
Very good. Thank you. Yeah. Otherwise, it can be any. Well, I'm using the wrong sponge. So what's the story of the sponges? Like this one is just not good, or
It's new because the old one,
the old one is better?
They all smell funny.
Okay, so much for the linear algebra. So now let's go back to the exciting geometry, of which we have all here. So, definition. So let's go back to manifolds. So say the submanifold. Now we need a good name for a submanifold. Say S and S. Okay. S as submanifold. All inside a symplectic manifold is called, and now either of these four things. So isotropic, or co-isotropic, or Lagrangian, or symplectic, any of the four things. If for all points in there, so all small s and big S, the tangent space inside the big tangent space is the corresponding adjective. Isotropic, co-isotropic, Lagrangian, or symplectic. Okay. Does that make sense? We use linear algebra to define this here using the tangent spaces. Okay, now examples. Let me swap the boards. Oh no, I see that the camera has been following me. Okay, that's not good. Hmm. Okay. Interesting. Because I turned it off. So. Well. Okay, good. So examples. So I will focus on examples of the like there is an easy example of isotropic, you just take 0. Subspace. There is an easy example of isotropic, which is means you take the whole space. Here as well. Take the whole space of 0. This is more interesting. So let's focus. This was not really a solid justification, but let's focus on Lagrangian for now, for the examples. They are the most intriguing ones, sitting at kind of the intersection of these two conditions. So, okay, so example. So if I take my cotangent bundle example, then there is a particular subspace. We know that the total space here is symplectic. But we also know that there is a distinguished subspace in here. Namely, we can take the 0 section. Okay, so this is the 0 section. So if you have principal bundles, and principal bundles not in general don't add with global sections. But vector bundles always do add with the global section and the 0 section. That's always well defined because every fiber is a vector space, and vector spaces have a distinguished element, and it's 0. So 0 section is Lagrangian. And an easy way to see that would be that use the thing I erased. So we know that the symplectic form here, it really looks like dpi dx out. And the 0 section in those coordinates would just correspond to setting p's to 0. So 0 section would be, in other words, this would be kind of the subset where we set all the p's to 0. And hence, okay, let's different color. So the thing I was going to write here before was actually correct. So the equivalent way to saying this thing is to say this is equivalent to saying that if you take omega and you restrict it to u, that you get 0. That's what it means, that if you put in any two slots in u, you get 0. Right? That's equivalent. Now translating it into the manifold definition, the equivalent condition for this thing is that if I pull it back to the tangent space, I get 0. But pulling back the tangent space at every point is the same as, in the isotropic case, the same as saying that the inclusion of omega is 0. So this is the I is the inclusion of S in. Okay, so that's kind of a useful thing to see. And a quick way to check if something is Lagrangian. Okay, so that's, sorry for this kind of a posteriori notation. So Lagrangianity, if you look here, Lagrangianity is to this condition, right? So you can say, let me say it here. So Lagrangianity, okay, I apologize very much, I have to insert it here. So Lagrangianity here is equivalent to the condition that it's isotropic and the dimension is half. U is precisely half. Okay, because Lagrangianity is really saying that I have this equality, I have a subspace, but it's more than that. It's not just a subspace; it's the subspace of maximal dimension, and it's the whole thing. So this thing ensures that it's U is inside here, and the second condition tells us that it's actually the biggest thing that can be in there, namely the whole thing. Okay, sorry for inserting it here afterwards, but please do think about this for a moment if it's not clear. So Lagrangian, to check Lagrangianity is enough to check if it's isotropic and if some numbers match, namely the dimensions. And hence corresponding to here, corresponding to here. So it's something that's Lagrangian if this thing is 0 and the dimension of S is exactly half of the dimension of M. Okay. Now let's go back to the 0 section. So are these two conditions true? Is it true that if I pull this thing to the 0 section, which essentially means setting this thing to 0, does omega become 0? Yes, because if I pull it back, I can jump with the pullback over the d's and I get precisely 0. So yeah, omega vanishes on the 0 section. Is it half dimensional? Yes, it is, because the dimension of this thing is twice the dimension of this guy, and the 0 section has precisely the dimension of M. So yeah, that's all that we needed to show. It's isotropic and dimensions match. Okay. Does anyone see another thing in here that's kind of, or a bunch of other Lagrangians here in the potential space? So I took the one out. I took out the one which was kind of horizontal in some sense. So what else can I do? Vertical. So all the fibers themselves are. That's the second thing. So the fibers are also Lagrangian. Precisely for the same reason. It is half dimension and they correspond to essentially fixing x to be some value. So it's kind of the complement to this. Okay, so now we have a bunch of interesting examples. Now, even more interestingly, and this I will, yeah, okay. So there is a nice proposition. And it has to deal with the modification of the first thing. So if you take our cotangent bundle, and now we take any section, any global section of this thing. So what does a global section look like? It's something like this, right? Now what is a global section of T star M? Section. Well, that's the same as one form, right? One form. Because one form are literally sections of T star M. It's the same as one forms. Okay, that's clear? Okay, so for instance, I take what happens if I take the one form alpha to be 0? What is the corresponding subspace? The 0 section. Thank you. So that's this example here, the green one. But more generally, I get something wobbly. Now the proposition says that this thing, let me call this subspace. So call it graph of alpha. Okay, that's a natural name for it. So the proposition says that the graph of alpha, which is a subspace of half, it's always of half dimension because it's a graph of. This is how M has some dimension. This thing has dimension of M and also the same amount of dimensions in vertical direction, so twice the dimension. So this thing inside T star M is Lagrangian if and only if it's closed. As a one form. Okay, it's a statement so graph of alpha inside here is Lagrangian if and only if, well, we already know that the dimensional condition holds. Like it is, because it's a graph of something from the section, the image of a section at this term is always half-dimensional. So the second thing holds. So let's check. This is if the Lagrangian if and only if the first condition holds. So we need to check that now that if I take omega and restrict it to the graph, to that submanifold, graph of alpha, and this is 0. That's what we need to check. Now, okay, but probably it's good to have some more concrete description of what does this graph actually look like. So the graph of alpha, this is simply, it's well, that picture, so it's simply the set of all so let me write it instead of saying it. So this is singled out by the condition that all the p's, they take the value which is alpha I of x. Does that make sense? So things up here, they are described in terms of some x's and some p's. That was our local coordinate picture. So there is some x here, and there is some x and p. And having a section means that I'm specifying the value of these p's, and having a section which is alpha, it just means that the p's are equal to the alphas. Okay, so this is by this I just mean this is kind of the set of points where p's are constrained to be this. Okay, and now let's calculate this guy. So in our local chart, this is simply dpi dxi. And now I want to restrict the whole of it to this subspace. So essentially I want to impose this condition that pi is equal to alpha ix. So I just plug it in, and that's how you restrict forms, you know, that's how you do pullbacks. You just literally express all these functions in terms of that. So what you get? You get alpha I of x wedge dxi. This is just a bunch of functions indexed by some I. So how do I calculate the differential of a function? I take a derivative with some other variable, let's say j, from this guy, by x, dxj, wedge dxi. And because the wedge product is antisymmetric, essentially you can put the antisymmetrization in here, and you see that this is vanishing of this is precisely the vanishing of the d of alpha. So this is maybe up to a coefficient which I somehow missed. This is like 2, I guess, 2 times. Is it? No. Yeah. No. It's 1 half. 1 half. 1 half. Whatever. It's 1 half. Okay. It's proportional to d of alpha with some number, maybe. So that's by vanishing of that is simply saying that the alpha is 0. Okay, we're almost at the end. I just wanted to formulate one more theorem which I'm not going to prove. And then we essentially exposed everything that I wanted to say about, oh, that's perfect, for this symplectic geometry. That might be useful to know for whatever life purposes you need. This is the basic symplectic geometry toolkit.
Different also physics generating function.
Yeah, that's I want to write a remark to that. Yeah. Yes, so as Werner is saying, note that so I can get Lagrangians if I take closed one forms on a manifold. But closed one forms are not very far from exact one forms. I mean, they differ by Well, they differ slightly if there is a first general cohomology on 0. But it's morally, or at least locally, it's the same thing. So, hence, if you have a manifold and a function of a manifold, then taking the d of that function, you get an alpha and you get a Lagrangian. So manifold with any function gives you a Lagrangian submanifold of the cotangent bundle. And you say that the original function was a generator of that generating function of that. Yeah, so let's say note. By starting with manifold n and a function, I get a Lagrangian submanifold of T star m given by graph of the f. And then we call f the generating function of that submanifold. That Lagrangian submanifold. Good. Now, one last thing, so we saw the big theorem, the Arbour theorem before, which says that things sort of locally have the same picture as far as the symplectic form is concerned. So now we can ask, like, okay, these Lagrangian submanifolds, they are in principle some interesting subspaces of my original manifold, symplectic manifold. So is it also true that, you know, that they have some sort of local form? And the answer is yes. This is the, here maybe I will, so, okay, I will call it Weinstein's theorem, but it's probably called Weinstein's Lagrangian tubular neighborhood theorem or something like this. So, yeah, Weinstein, I will call it Weinstein's theorem, to at least preserve the name. This thing says that, this thing in a sense says that all Lagrangian, if you only look at the underlying symplectic form and the underlying Lagrangian manifold, then they actually all look as the green picture above. They all look as the zero section of the tangent bundle. So to make it formal, so let B, let L be a Lagrangian. Note that I'm calling it L, not S, because it's not Lagrangian, because of emphasizing the Lagrangianness. Lagrangian submanifold of F of the symplectic manifold. Then there exists an open neighborhood U of L. Also, there exists an open neighborhood V inside T star L. So I now forget M and just focus on L and take its cotangent bundle. And I want to have an open neighborhood of the zero section. So this is just, okay, so there always exists a local neighborhood around L itself. This is L, this is M. So there exists some neighborhood here, U. And there exists another space, which is just this T star L, which has this zero section inside, which is the zero section you can identify with L, if that was not clear, I forgot to say that. The zero section is essentially the same as the underlying manifold. And there is also an open around this, some V, such that, and there is a symplectomorphism relating the two. So let this be that. Then there is an open neighborhood one, an open neighborhood the other one, and a symplectomorphism U to B, sending L to the zero section. prove this, you need to employ like the Mozart trick, some tubular neighborhood theorem, and other fancy stuff, but it's doable. So okay, so this tells us what locally Lagrangian submanifolds are. And you see, it's kind of a cool thing because it says that, okay, this is just note. But suppose that you want to study a difficult problem in general, but you have a symplectic manifold. Let's say it's compact, because those are kind of the most exciting ones. I mean, none of our examples was compact. But you can imagine compact examples. And you have a Lagrangian submanifold, so somehow dimensional and isotropic submanifold, and you want to study the deformations of such a thing. And you can kind of imagine that locally this thing has to look like this other picture, which is kind of more rectangular, more cubey. It's just like more vector spacey. It's like a V star L, and you have this, and you imagine that you want to study deformations of this, which are still Lagrangian. So there would be some sort of, picture like this. In this picture, there would be something like this, and and as long as you don't do some funny stuff like this, as long as it remains kind of a section of something, then you know that that section, this thing will be given by this right thing will be given by some one form on L, which is closed. So, and even more, if L is simple enough, so it doesn't have first cohomology or something, then this is essentially just function on L. So in other words, deformations of Lagrangian submanifolds can be described in terms of objects which live on L, namely functions or closed one forms on L. Kind of a cool fact. Okay, any questions for this part? Let's make a break. If it's too cold, then tell me, I can close the window. Okay, so that concludes the symplectic part. And then before digging into current algebras, which are supposed to be generalization of things that people care about, then we need to continue introducing things that people care about. So let's do Poisson geometry now. The symplectic one was kind of the most important one, so that there I really went into detail. So this thing is a sort of like a larger class of geometry. So I will only say a few things about it, but they might be useful or fun. So first, the definition. So a Poisson manifold. So this is the thing that we saw at Thomas's talk before. Poisson manifold. Is a pair m and pi, so not omega, but pi, of a smooth manifold m and pi, which will be a section of the wedge 2 of Tm. So such a thing is called a B-vector. So it's like a form, but it's not a form. It's a B-vector. So it is antisymmetric, but it doesn't have indices down, but indices up rather. Such that when we consider the algebra of smooth functions on the manifold, together with the Poisson bracket, which is induced by this, I will say how in a moment, namely now. So with the Poisson bracket being defined simply as this. So I take the two functions, differentiate them to get one forms, and then I just pair them with the vector. So this pair, with the bracket defined this way, is a Lie algebra. Namely, the non-trivial thing to check is whether it satisfies Jacobi, because Lie algebra needs to satisfy Jacobi or Jacobi. And it needs to be antisymmetric, but antisymmetry here is guaranteed by this wedge here. The non-trivial thing is to check the Jacobi identity. and then phi is called the Poisson vector. Poisson vector. Okay. So, example. Any manifold with a zero vector is fine. Now a little less boring example. Let me phrase this a proposition. So if m omega is symplectic, then we can take m and we can invert omega to get pi. I will comment on that in a second. This is Poisson. So what do I mean by inversion there? Well, first of all, if you put it in a frame, and this is some bunch of matrices, so you can invert the matrices. But kind of more invariantly, so remember that omega, which is really, let's say, we are at a point, so I will, at every point, this thing is a two form, but in particular, it lives in a tensor. We can see there's a living in P star m tensor P star m. And hence we said before that we can equivalently see it as a map from Tm to T star m. And we wanted this map to be invertible. That's how we define non-degeneracy of the Poisson structure, of the symplectic structure. I called it probably omega before, but let me now distinguish it a little bit. Let me call it properly. So I mean, it's the same object, really, kind of, but here I want to see it as a map, so let me call it like this is omega flat. Is that the flat one? Because I am vector and I lower the index. Okay, so now when I say that I invert it, like abstractly speaking, what I really mean is that I invert this map. So instead of this map, I invert it because it was invertible. And I obtain something that I will call pi sharp. Because again, index down, we raise it. That's why I could call it sharp. But this thing is the same really as a map, as an element in wedge 2 Tm. Sorry, in general TMM. I haven't used antisymmetry so far. This is just to say that whenever I have a covariant tensor of rank 2, which is an element of this, I can see it as a map like this, and if it was non-degenerate, then I can invert it, and then I can correspondingly see this as an element here, where I simply plug in things in the first one. Now, so all that, okay, so what we need to prove is, now at least this construction is hopefully clear, what it means to invert this thing. What we need to check is whether this is Poisson, so if it's antisymmetric, and if it's really a p-vector, and if it satisfies that thing. So, how do we prove this? Proof. Okay. Let's calculate this thing, which is how we define this thing. So this is what we want to show is the algebra, and also antisymmetric because it's. So what is this thing? In other words, if I want to go up, I want to now use this thing. If I now go to pi sharp, then this is the same as saying that I take my df, I plug in df into my pi sharp, I get a vector, and then I pair that vector with the one form dg. Okay, but now this thing is the same thing as this omega flat inverse, acting on df, and then paired with dg. Okay, but now remember the crucial formula that whenever you have a function f, then you can define the Hamiltonian vector field, which we call xf, like this. And this is precisely, if you write it in this flat sharp thing. This is the same as saying that if you take minus the f and then you apply only omega flat inverse, then you get xf. And I take the f, and then you use the inverse of the map which sends vectors on forms. So you already use this thing. So in other words, if I go up, or maybe I should, okay, so let me sneak in a sneaky minus sign here. Okay, there's a minus here. Sorry for changes. So here it means that I define pi with a minus, so now there is a minus. And that minus was introduced for the purpose of killing this minus. So this is the thing that you get is simply xf acting on dg, which we know is the same as xf acting on the function g, which is simply the definition of a Poisson bracket using like the symplectic form definition. Symplectic forms. So this is the Poisson bracket, which we define in the language of symplectic forms, and that one we know for sure satisfies. It gives a Lie bracket, and hence our original one is as well. That's it. Okay, any questions? So in a sense, you can see symplectic manifold as being a subset of. This was one of the pictures we had before. Poisson, and there was symplectic. And now you can see how they fit. Any symplectic is Poisson, but not every Poisson is symplectic, because it's only the ones that come from invertible omega. So for instance, the first example of 0 Poisson vector, that was not symplectic. Very much not symplectic. Okay, now, but there is more relation between Poisson manifold and symplectic manifolds. For instance, we phrase it as another proposition. So this proposition will tell us that if a Poisson manifold is well behaved, then I can regard this as being kind of sliced, like foliated by some submanifolds which are symplectic. There's some sort of foliation of by lower dimensional submanifolds, which is where all these things are symplectic. For instance, in the trivial example, those submanifolds are just points. And in the second example, the submanifold is the whole manifold. So, okay, so what does this thing say? It says that if you have a Poisson, so suppose okay, we take the image of pi sharp, I guess. This thing is something that at every point it lives in the tangent bundle. So together it's a subbundle of the tangent bundle. Okay, so image of this map is somewhere here at every point. So if I collect it over the whole manifold, I get a subbundle. So and I call it D. D for distribution, because subbundles
It's just for regular, right?
yes, I want to say that okay, suppose this thing has constant rank. Which just means that at every point this thing has the same dimension. So for distribution we require its constant rank, is that right? Or okay.
Like regular distribution.
Okay. Well, since I didn't call it distribution in writing, then it's fine. Thank you. So suppose that this thing has a constant rank, so this is what I meant by well behaved. Then this is an integrable distribution indeed, in fact, integrable. Which means that if I take any two sections of this distribution, so any two sections which is sit in this subbundle at every point, and I take a bracket of them, then it will also be that maybe I should call it involutive, but integrable is probably the same in this context. You know, it is. Okay. Right, sorry, so this thing is integrable. The Poisson B vector is tangent to the integral leaves. Those things. Integral leaves.
If it wasn't integrable, you would not have a root.
Yeah. Yes, that's why this sentence goes after this one. and actually on these leaves, this thing becomes invertible. So this and leaves are symplectic, meaning that this pi on the leaves it is tangent to them, so it defines pi on each individual leaves, but it's not just any pi, it's actually an invertible one, so they're symplectic. So the gist of the proof. So what we want to show is that if you take any two things in here, so let's say, okay, need to show this works together. Okay, so we need to show that we have something in the image of these things. So if we have like an image of, if we have a pi sharp of some alpha and pi sharp of some beta, where alpha and beta are some conforms, then we want that this thing is again in the distribution. So this thing is again in the image, the section of the image of pi. So this is in the how did I write this? Okay, let's say the image of pi sharp. So we want that it's again pi sharp of something. Unfortunately, if you want to check such a thing, so this is what it means to be integrable, and if that or involutive, and if such a condition holds, then you know that there is that you can foliate your manifolds into such leaves of lower dimensional submanifolds, such that each of these things is its tangent space is precisely this D. That's what it means to be integral leaves. And here I'm assuming a simple case when this constant, when we have constant rank, so there is no like jumping of dimension. But technically we need to verify this condition. And actually, if you think, okay, what this follows from a slightly weaker assumption thing, like if we manage to show that this thing is true for sections of special time, which actually generates the whole subrumble in a suitable way. So if we manage to show this not for every one form, but only for exact one, then this is actually enough. Because any one form can be written as coefficient functions times dx. So you can always reduce it down to this. Okay. Okay, what is this now? So, so let's prove this second thing, which is easier. It's easier in particular because we know what these things are. So this thing, well, if you follow the proof until here, then you will see that, sorry, pi sharp. That pi sharp of df is nothing else than the Hamiltonian vector field for f. Okay, so if you ignore the dg, then what we did is that we looked here, and then here, and then we added the dg. So filling it in the first slot, the df is the same as taking the Hamiltonian vector field. And so the same thing in here. And hence we know that the commutator of two such things. Alright. No, actually we don't, because we only know it for symplectic technically. Right. Okay. Okay, I realized there was a step that I forgot to do. Anyway, let me use the convenient dot notation. We say that z is equal to pi sharp of
With Poisson.
of d of the Poisson bracket. Thank you. And hence it sits in here. The dots. Okay, I forgot that I haven't proven the corresponding thing for Poisson. That the commutator of Hamilton and vector fields in Hamilton. Anyway, you can try to.
It's just using the Jacobian.
Thank you. Yeah. Right. Okay. So not hard, so you can try to do this if you're interested. But anyway, this is a little bit aside from what I want to focus on, but it was kind of again a bit not to mention it. Sorry for this, but yeah, thank you. Use the Jacobian and the Poisson bracket to prove the dots in here. And okay. And anyway, I didn't want to show the whole proof, so then the rest. Okay. This was just a sketchy thing. Anyway. So this is just to say that Poisson manifold, which are well behaved, they're kind of foliated by these things. Also, a little bit more general, not just for constant rank things. There's also many non-constant rank situations. Is it in general?
Yeah, it's general.
It's general. Okay, thank you. So yeah, even if you relax that, then you get like a singular distribution with leads of different dimensions.
There is an analog of that rule.
Sorry? Yes.
Analog.
Well, no. I mean, there is a Weinstein splitting theorem,
Yeah.
but that one is like, I mean, these things locally are not even known. Like you can show that it's locally always symplectic times some Poisson which vanishes at a point, I think.
Yes. Right.
But those ones are unknown.
X and P and something which commutes with everything. Like Casimir, essentially, right? And something which commutes with everything. I think that.
I think so. I mean, as far as I know, it's still like unknown. It's always there's a theorem which is always like symplectic. Locally, it's a product of symplectic and a simpler Poisson in the sense that it's vanishing at a point.
Yeah.
Yes. But the Poissons vanishing at a point are kind of wild. Yeah. So you can show that the linearized part of it always defines a KKS bracket, and if that KKS bracket, if the Lie algebra is something like a compact or something.
Normal form.
Sorry?
This is what people call normal form.
I think. Well, this is called Weinstein splitting theorem, I think. But as far as I know, this is still like it's like vastly open still, because the second bit that you have, so symplectic times some Poisson vanishing at a point, but Poisson vanishing at a point can be very wild, and it's only known that in some cases, if the linearized part of it defines an algebra which is well behaved, like I forgot unimodular or something, then you know that you can linearize it.
I thought that you have always like local around the point local coordinates like x's and p's and some f's, and the f's commute Poisson commute with its x's and p's, and x and p's commute with Poisson bracket delta and j, but maybe.
I mean, maybe because also the thing you're saying is not like an explicit thing. It's more like it doesn't say it has to look. I mean, there is still some freedom in that.
Because there are like coefficients for these steps, right?
Yeah. Okay, yeah, then it's probably the thing. Yeah. Thank you. Okay, so sorry, this was just for illustration. Now probably the most important examples of the theorem, which is not symplectic. And that's the dual of the Lie algebra. So it says that there exists a unique, okay, so fixed Lie algebra G. The claim is that there exists a unique Poisson structure, so Poisson manifold structure on the dual of that. So this is a vector space, but now I want to regard it as a manifold, because vector spaces are manifolds in particular. So there exists a unique Poisson structure G star, such that I prescribe how it looks, how the Poisson structure, how the Poisson bracket looks on special functions. So such that for any x and y which are in G. Now elements of G can be regarded as special class of functions on the dual, right? Because linear functions on the dual. So if you give me, so because G is the star of G star, so any function, any x gives me a function which if I, so if I want to, okay, any x gives me a function which I would call f of x is a function on G star. I'm just describing how this inclusion goes. And the function is simply defined by the fact that if I look at it at a point xi, where xi is an element in G star, then this is just the evaluation of xi on G on x. So. In other words, functions on elements of the dual are linear functions on the original space. So these things are so elements in G provide a very, very special class of functions on the manifold, which is G star, and I require that for any such things, the Poisson bracket of these two functions is equal to the commutator in G. Okay, so is the statement clear? Like, if I have a Poisson structure here, Poisson structure is the same. Poisson structure gives me a way to calculate Poisson bracket, and I demand that the Poisson brackets are given Poisson brackets on these guys, and these guys are very special, but in a sense they generate the whole algebra of smooth functions on there because they're linear and everything else. You can build all of them at least up to some completions and things. So right. So in a sense, it's enough to define it on those things, and I define it on those things. It gives the Lie algebra. It coincides with the Lie algebra bracket. The Lie algebra bracket gives me yet another element of Lie algebra, which is again a function of the same class. So this is kind of an important class of examples. And I can be more explicit. Let me just say that this is what is referred to as KKS Poisson structure. It also has other names, the linear, and other names.
If you're French, then it's just S.
Yeah.
Really? Oh no. Okay. So this is the Kirillov constant Suryo. Okay, to be a bit more explicit, so if you like explicit formulas, then let's say here, so any basis. So if you pick any basis EI of G, then again bases are just a bunch of elements in G, and elements in G I can identify with functions. So in fact, so any basis can be regarded as coordinates on G star. You give me an element of G star, I pair it with any of these and I get a number. So that's precisely what coordinate is. Think about it. If you like. Okay, so now I have a bunch of coordinates on my space, and then the claim is that this Poisson bracket looks as follows. So if I maybe have to sign, but signs are irrelevant anyway. Okay. So remember, these things are just coordinates, and these things are partial derivatives with respect to those coordinates. And I use the wedge, although wedge is usually reserved for forms, but this is really the same thing as forms, except it has upper indices. So the same formulas work for wedge. It's just the anti-symmetric combination. And these are the structure coefficients of the Lie algebra. So, and it is for the reason. So if you look at the the components of this tensor, then the components are those things, where these things are some numbers, constants, but these things are functions, coordinates, linear coordinates. So that's why this thing is called the linear Poisson bracket, because the coefficients of the Poisson bracket of this Poisson tensor, which is these things, they depend linearly on the coordinates. Okay, and now just one exercise. Okay. So try to think about what are the symplectic leaves of this. So calculate pi, the image of pi sharp, and show from this that symplectic leaves are precisely the coadjoint orbits. Okay, so in other words, you have G with the algebra. If you integrate it to a connected, let's say integrate it to a connected, simply connected leaf, and that this thing acts on it by the adjoint action, and hence it also acts on dual. So it acts on here. This is called coadjoint action. And this thing will decompose this space G star into orbits of this action, and those orbits precisely correspond to symplectic leaves. So this is in fact the important source of symplectic spaces. They are precisely coadjoint orbits of the coadjoint action. Here's one example. If you take G equals to SO3. Now G star is the dual of that. But because SO3 has a natural killing form, a natural non-degenerate pair, you can identify this guy with SO3 itself. So if I want to draw the picture of G star, I can just draw the picture of SO3. And the way the big group SO3 acts on small SO3, if you think about it, it's precisely the same way it acts on three-dimensional space. So it's really rotations. So and orbits of rotations are spheres. So these are the. It was a bit fast, but anyway, in this example, the orbits are spheres, except spheres of increasing radii, and in particular, you get the point at the origin. So all of them are two-dimensional, except for the point which is zero-dimensional. So that's an example. So these are all symplectic, but together they assemble into a nice Poisson structure, which is described in this Poisson thing, and it's a Poisson structure on SO3. Okay, and there was, I think, one last thing I wanted to say about. Hey, any questions? I need to erase this down. In a sense, this was a very condensed course or not really a course, but like a condensed introduction into some aspect of symplectic and Poisson geometry. And although we might not need all of it, since I'm talking about it already, why not? Especially now it's recorded, so people can look at it online if you wish. So one last thing I want to say about Poisson manifold, if there is no question, would be a sort of alternative way to reformulate the Poisson condition directly in terms of the Poisson vector. also this thing will make a link with what Thomas was saying, but anyway, that won't be important. Anyway, so okay, so let me just one last thing before this thing dries up. So we define the thing. I think Thomas called it T poly. I will call it same as vector field of poly. Define this thing to be all multivector fields, so sections of wedge powers of M. Of course, this thing will not go to infinity, but only to the dimension of M. But so this is like in the zeroth order, the 0th degree, these are functions, then it's vector fields, then it's B vector fields, and then you can go higher, you can call them 3 vector fields, quadrant vector fields, something, I don't know. So,
It used to be called multivector. So before consideration.
sorry?
I think it used to be called multivector.
Really?
Before consideration.
Ah, okay. So polyvector or multivector. Okay, so let me formulate it as a proposition. So this thing is the almost the end of this Poisson part. So this thing says there exists. Okay, I'm formulating it in this way to save time and space. So there exists a unique bilinear operation. Let's say we specify that bilinear, I mean bilinear of real numbers. Bilinear operation. I'm wondering if I should give it some other name, but let me just save space and write it as a bracket. It goes from here. So there is essentially a bracket. That's fine. There is a bracket which should coincide with what we briefly saw before. So there is an operation of degree minus 1. Okay, so a remark on the side. Degree minus 1 means that if I have A, which is of degree, well, if I have A and B of some degrees, then the degree of this thing will be the degree of A plus the degree of B minus 1. That's what it's meant, that an operation is of degree minus 1. Take two things and you take the result. It will be not just the sum of degrees, but it will be shifted by whatever the degree of the operation is. Okay, and by degree, of course, I mean this I here, whether it's a vector field, B vector field, 3 vector field, etc. So the claim is that it's a unique linear operation of this degree such that it satisfies some properties that fix it. So, for instance, for all vector fields, the bracketing is the lead derivative with respect to B. So now why is this a degree minus 1 operation? Because lead derivative we saw before, differential forms, lead derivative with respect to B doesn't increase, doesn't change the degree of the form. And why is it here a degree minus 1?
Vectors are of degree 1.
Yes, exactly. Because now there is a left-hand side. Being of degree means that I compare the degree of the constituents with the degree at the end, and I note discrepancy. So if I put something like polyvector field of degree n, then the result here will be polyvector field of degree n, because the derivative doesn't change the degree of that. But because there was a vector field here as well, and there is no, there will be degree of A entering here and 1. So it's okay. That was not very important, not just to confuse everyone. Okay, so I want a vector field with this. I want that it is antisymmetric in some sense. possible things. I want that if I act on the wedge product, and this thing is A, B, wedge C plus minus 1 A minus B wedge C. Okay. An arguably complicated definition. Also, you might remember from before I was mentioning this thing about the Koshul signs, saying that if you commute two things, then actually figuring out signs is very easy. You just multiply whenever you switch two things, you multiply the minus one to the some product of degrees. Now, why doesn't it work here? It seems that something is off because there is not just multiplication. There is some minus one, and there is some parentheses. There was supposed to be degree here. Degree A. So more of a philosophical equation. More philosophical question: why doesn't it work here? It does. Okay. Yes, it does. It does, but no one knows. You will need to shift the degrees because I mean, this is not. This would be the Koshul sign if this would be dig A and this would be dig B. So this thing tells us that actually what we really should be looking at, we should be shifting the whole thing. We should be really going to the degrees. It will be not these degrees that we see here, but we should be kind of moving them a little bit, and then we might get like the Koshul sign in that simple form that I discussed the other day. And indeed, we will later on come to this object in a sort of much more natural way, where you don't need to remember any terrible formulas like this. But okay, is the uniqueness part of this statement clear? So, is it clear that if such an object exists, then it is unique, if it satisfies these three things? Any ideas?
So the first thing specifies is when one of the inputs is a vector field.
Mm-hmm.
The second thing says that it doesn't matter which one.
Mm-hmm.
And the third thing says that you can always reduce it to that case.
Perfect, thank you. And what about function? What if you have function times function? What if you have a bracket of function? It works, yeah? Your argument is perfect, apart from the one case. What happens when there is a function and a function?
There are no minus one.
Exactly, so that's zero. For the degree reason, that is zero. So it's specified fully. And in fact, you can write down an explicit formula which shows the existence, if you wish. But now the last proposition with which I end this wasn't good is that let's say phi a B vector is Poisson if and only if phi is 0. So that's kind of, if you talk to Poisson geometry, then they tell the Poisson structure is such that it satisfies this. Where incidentally this bracket is called the Schouten bracket. Do people also call it Schouten universe?
Yes.
But they also sometimes call it the Schouten bracket, right? Okay. Schouten or Schouten universe.
Call it one of the derived brackets.
Sorry?
One of the derived brackets.
Okay. Okay, or that.
Also corresponding to the old symplectic structure.
Yeah, we will get there. We will get there. So yeah, that's kind of it for this bit for Poisson, and then there is I think there is an ideal amount of time to talk about complex manifolds, namely 15 minutes or so. Me and who is. Pronounced. You mean pronunciation? No, it's not my house. But what one before? No, you said
Yeah, it's Dutch.
It's Dutch and in Dutch.
Are you sure? I mean, sorry for those that are watching online. Really? I always thought it was not nine hours. Something like.
As much terrible as you can pronounce it.
Okay, so the most American.
You never get it right.
Okay, it might. Look, I might cut this from the recording.
It's like, how that?
Okay. I see that. I should have just written them and not pronounced. Yeah, maybe one thing that I forgot to mention with the symplectic is that there is an option of a pre-symplectic form. Just to complete this kind of thing from the sketch on the first day. Pre-symplectic manifold. Pair. Where this thing is now closed to form. When you realize the non-linear RCN instead you require that the kernel omega is constant. Sorry, that has constant rank. Or if you use kernel omega flat. So there is a more general version. Sometimes people forget about the second condition. They just say that if it's closed, it's pre-symplectic. Okay. Then last time a 10-minute introduction into complex manifolds. And then we can start with random algebra next time. So let me just repeat that all of this is, well, not a restriction necessary, but its purpose is to introduce these classes of geometry before we see next week how they are sort of nicely unified in general geometry. So, okay. So this is last part one, and I call it complex manifold. Complex geometry, manifold, okay, whatever. And I essentially only want to get to one statement in the end, but let me, anyway. So what is the idea? Without going into too much detail, you can imagine that it's the same as with smooth manifolds. So you have a topological space of some desirable nice properties, and you want that locally there is maps from this one into Cn. So not to Rn, but to Cn. And you want that if whenever you have an overlap, then the transition functions on these things are all log. Although this sounds like a very mild, very small step going from smooth manifolds, it's actually a very big step because these things behave very differently due to the fact that they don't have partitions of unity. The homomorphic functions are kind of difficult or like uninteresting. And typically you want to describe this with a different color for purposes that will become later. So this is how I write Z, if anyone is confused. So you have some bunch of Z's as complex coordinates, but if you wish, you can always break it to their real and imaginary parts. So the complex manifold in particular gives rise to a real manifold, where the charts will be simply going to R to 2n, when instead of having a bunch of Zi's, we will have these guys. And before saying what I want to say, let me just say that in studying this, it's kind of useful to distinguish several notions of tangents. So there is like particular nice way that I like is to say that there is 3 different versions of a tangent space at any point. So first there is what I would call a real tangent space. So this is the if you don't work actively with complex manifolds, it's according to what I do, then sometimes it's good to sit down and break things into details. So this thing really just means that they take the underlying smooth manifold. So this thing always gives rise to a smooth manifold. Okay, in particular. So I just take a smooth tangent space. I will denote it by R. Putting it here. And there exists a thing which is called a complex tangent space. And this thing I define to be a complexification of this. Okay. Note that this thing on the top, this is a vector space over real numbers, and this thing is a vector space over complex numbers. And there's a third guy, which is called the holomorphic tangent space. That one I will denote T01 of M. And this thing is defined abstractly. This is a complex subspace of the second guy. So this is the holomorphic tangent space. And this is again a complex. I will have to say how this is defined, but this is complex. And this thing is, if I define this, I define this, and this thing is defined as derivations. If you want to have an abstract definition, independent coordinates, you can say this is derivations vanishing on anti-holomorphic functions. And then you may ask, what are anti-holomorphic functions? Well, I hear you. Anti-holomorphic functions are functions f such that the complex conjugate is holomorphic. Okay? And that makes sense on manifolds of this type. So the reason I'm doing it in this sneaky way is that I'm trying to not talk about coordinates, and that is trying to talk about, to say as much as possible about the kind of using this holomorphic map, the holomorphic charts things as much as I can. So that's how you can describe those things abstractly. Starting writing these red coordinates, let me say that in terms of these things, this guy is simply the span of partial x and partial y. The second guy is the C-linear span of such things. And the third guy is the C-linear span of something that I will call partial z. There's i's everywhere. Where as maybe subtle as this might be, this thing I'm defining here to be 1/2 partial xi minus I partial yi. So the kind of formula that you would I'm saying that I'm defining this because here I'm using the fact that z is x plus iy. I'm putting some i's, not to be confused with big I. And I'm using the fact that you can define a second guy, which is called like this. And if you treat this as a real change of coordinates and you express z out of x and y, then this is what you land up with. But because that is not, one has to be careful here, so I'm really saying that I'm defining this object in this way. Abstractly, it's this. But if you write concrete formulas like this, then if you ever wonder what is the meaning of this, then it's this. But okay, be it as it may, I decided to go to this non-standard, or maybe not, maybe it is standard, but anyway, I find this more clarifying than and I also want to avoid the endomorphism J notation for reasons that might become clear later. But now note that because this guy, second tangent space, was really a complexification of something real, and this thing has a well-defined conjugation. Complex conjugation. And indeed, if you calculate what this thing is, what is the conjugate of this guy, you will get another bit, which I will define to be 0, 1 of m. And this T0, 1 of m is in fact transverse. And together they span the whole thing. Span the whole complex thing. Okay, and right, and if I want to add this red stuff in here, then I can say that this thing is again C linear span of partial z bar I, where partial z by I is simply the conjugate of that, so it's partial xi plus I partial yi. So the bottom line of all this is that I having a complex manifold, if I see it as a real manifold, then I get a spatial structure of my real manifold, namely, okay, so punchline. Starting with a complex manifold, I get a spatial complex subspace of the complexification of its real tangent vector space. And this spatial subspace is this kind of space of holomorphic direction. This one, holomorphic tangent space. And this suggests a way to think about complex manifolds without talking about complex charts. Namely, you start with a real manifold. So just here I already see it as a real manifold. So you start with a real manifold, you complexify the tangent space, and if you manage to find a subspace of that with some desirable properties, then you might hope that that subspace actually will be T10M for some complex structure. Okay, does this make sense? This is a little bit subtle, at least for me, whenever I think about these things. Try some quickly. Just to finish, let me now collect this into a definition. So an almost complex manifold hopefully visible, which is kind of one step less. Because if you take this thing and you try to make it into almost complex manifold, try to realize the anyway. I'm trying to find a natural way how to realize the definition, and that goes as follows: an almost complex manifold is a smooth manifold, not complex, smooth, together with, and now many people would say J tensor satisfying some properties. I don't like that, so I will instead say together with a subbundle of the complexified tangent bundle, subbundle, such that L this width is 0 and L plus L per bar is the complex.
Do you not want them interchange the complex conjugation as well?
Sorry?
Do you not want the two guys?
Oh yeah, sorry. That's kind of very good. I mentioned here as a definition of L bar. So such that
Okay, sure. No,
defining
it's by definition of the
L bar to be the complex conjugation.
Sure.
But yeah, it's good to emphasize complex conjugate of L. So Okay, so in the case above, this will be the T01, T10. And maybe just a remark. So normally, what people do, people talk about, people instead of saying this, they instead write, they encode this data differently. They say that you have a tensor J which goes from Tm to Tm and which squares to -1. And then these things, and then this L is defined to be the I eigenbundle of J. It's precisely the same data. Or at least it should be. This condition and those conditions. It's just that I, also for the Courant purposes, I want later on, I find this first one kind of better, and also I find this a bit, I don't know, sketchy. I mean, it does have this property which kind of leads you to think that it looks like complex numbers, but then if you think about how this acts on like dz, it acts by multiplying it by I, and dz bar it acts multiplied by minus I, and it's like, you know, I mean, it makes sense, but I don't know, this is more geometric somehow. I find it's maybe more geometric. Okay, and then the theorem, and that's where we end. Theorem, the big one. Newland and Nuremberg. Says that the normal complex manifold. Intermediate definition. Sorry. So an almost complex manifold is called integrable if there exists a complex manifold structure on M such that L is T10 of M. So if it actually comes from a complex manifold, if this L comes as a T10, then you call it an integrable thing. That corresponds to some proper complex structure which satisfies some integrability criteria. But now, okay, the big theorem says that an almost complex manifold is integrable. There is an easy condition to check. Is integrable if and only if L is involutive. Which means that if you take two sections of L, you have one section and another section, and when you take their commutator, then this thing will be a section of L. And here, of course, I'm the commutator vector field, it lives on sections of Tm, but here I'm just extending in the obvious way to allow multiplication by complex numbers. See linearly. So, yeah, so there is some sort of involutive distribution in the game in some sense. Not in the usual sense, where you have a subbundle of tangent bundle, but now you have a subbundle of the complexified tangent bundle. But it still satisfies the involutivity property, and that thing is equivalent to something nice, namely that it descends from a proper complex manifold structure. So yeah, thank you. That's what I want to say. Oh, okay.